So today's video is all about practicing computing problems with partial derivatives. So now that we know kind of the intuition behind what partial derivatives are, let's get right into some questions that are asking us to solve partial derivatives and verify some theorems we'll go over. Okay, so let me just change my pen color here. Okay, so find the first order partial derivatives f sub x and f sub y for f of xy equals y divided by x. Okay, so before we even get into this problem, I'm going to rewrite the function f of xy. I'm going to rewrite it as y times x to the negative 1. So I'm going to write it as a power instead of a fraction. And anytime you do this, anytime you change it from a rational function or a fraction into kind of a series of powers, it'll just make it a lot easier to take the derivative. Okay, so f sub x, this notation here just means what's the partial derivative of f with respect to x? Okay, so f is y times x to the negative 1, right? That's our function, and we're taking the partial derivative of the function f with respect to x. So we're going to leave y constant, right? Because it's a partial derivative. Our variable here is determined to be x. So if our variable is x, that means y is a constant. So remember, when we're taking the derivative, we bring down this exponent to the front. So this will be negative 1 times y. So negative y, right? X to the power of negative 2, right? So anytime we're taking the derivative of an exponent or a power, we're bringing that exponent down and reducing the exponent by 1, okay? Now let's do f sub y. So partial derivative of f with respect to y. So it's the same kind of idea here, right? We're leaving x constant now because our variable that we're differentiating with respect to is y. So the x to the negative 1 is going to stay the same. We're going to pretend like that's just a constant, and we're going to differentiate this y here. So the derivative of y is just 1 with respect to y, so it's going to be x to the negative 1 times 1. And that's just going to be x to the negative 1. We don't need to put the times 1 there. Okay? So that's the first question there. Find the second order partial derivatives for f of xy equals y over x. So this is the same function here. Okay, verify Clairaut's theorem that d squared f over dxy, or partial squared f over partial xy equals f sub xy, which equals f sub yx. Okay, so lots of kind of weird notation, but all this is saying is we're going to find the partial derivative of this function here. Okay, we're going to find the partial derivative, and then we're going to differentiate that partial derivative with respect to the opposite variable. And we're going to see if those two things are equal, okay? So I'm going to rewrite the function here. F of xy equals y times x to the negative 1. Remember, we're going to write that as an exponent. Okay, so f of xy, the order that we differentiate this is going to be from left to right. So we're going to differentiate it with respect to x first. Okay, so we're going to differentiate the function with respect to x. Or we need the curly d, so df over dx. And then we're going to differentiate this whole quantity here with respect to y. So we're taking the partial derivative with respect to y of the partial derivative of f with respect to x. Okay, so partial f by partial x, that's going to be the derivative of this with respect to x, so we're leaving everything else constant. And remember, we did that up here. It's going to be negative y times x to the negative 2. Okay, so I'm just going to kind of plug that in here. Negative y times x to the power of negative 2. Okay, and now we're going to take the partial derivative of this with respect to y. Okay, so let's just think here. If we're taking the partial derivative with respect to y, that means we're leaving the x to the negative 2 constant because we're pretending like it's just a number. Okay, so the derivative of negative y is just negative 1. Okay, so it's going to be negative 1 times x to the negative 2. So that's really just negative x to the negative 2. Okay, so this is the partial derivative. This is f sub xy, negative x to the negative 2. Now we're going to try and verify Claro's theorem by kind of differentiating it in the opposite order and seeing if it's equivalent. Okay, so this time we're doing partial partial of partial f over partial y by partial x. Okay, so going partial by partial x of, okay, so what's partial f over partial y? Well, last time we did partial f over partial x, and when we did that, we just left everything that wasn't an x constant. In this case, we're doing the same thing, except our variable is y. Okay, so our function is right here. We're going to leave this x to the negative 1 as our constant. Okay, so x to the negative 1, that means that we're going to have x to the negative 1 here. Okay, because the partial, or the derivative of y is just 1, and we're leaving x to the negative 1 as it is. So now we're going to take the partial derivative of x to the negative 1 with respect to x. So remember, we're going to bring the negative 1 down in front, and we're going to reduce the exponent by 1. So it's going to be negative x to the power of negative 1 minus 1, so negative x to the power of negative 2. So since these two are the same value, we kind of verified Claro's theorem for this function here. Okay. Determine f sub xyx for the function f of xy equals 4y squared x plus 7x y cubed minus 2e to the x minus y. Verify that it can be equated to f sub yxx. Okay. Okay, so f sub xyx. So that means that the first thing we're doing is we're taking the partial derivative with respect to x of the partial derivative with respect to y of the partial derivative of f with respect to x. Okay, so let's just kind of do this one step at a time. So this is going to equal, we keep kind of the first two terms the same. Now let's find df by dx. So for this function, it's a sum of three different expressions, so we can split it up into three different derivatives. What's the derivative of 4y squared x with respect to x? Well, remember, if we're differentiating it with respect to x, that means we're leaving everything that's not an x constant. So the 4 and the y squared are constants. Anytime we have a constant times x and we're differentiating it, it's just equal to that constant. So it's going to be 4y squared. Okay. Except this isn't the whole derivative. So then we have to add the derivative of 7xy cubed with respect to x. So that's going to be 7y cubed for the same reason. Okay, and then we have minus 2e to the x minus y. So remember, if we had 2 to the power of, I'm just going to pretend y is a number, right, because we're treating a constant, so e to the x minus 1. The derivative of this is just itself, 2 times e to the x minus 1, because by chain rule, we have to differentiate like we have to take the derivative with respect to, say, u of e to the u, which is e to the u, and then we have to times it. We have to multiply it by the derivative of u. Okay, we have to multiply it times the derivative of u. Okay, and the derivative of x minus 1 is just 1, right? Because the derivative of -1 is 0, the derivative of x is 1, so it's just going to be itself. Okay, so it's going to be minus 2e to the x minus y. Okay, so now let's take the derivative of this, all this stuff on the inside, with respect to y. So we're leaving the x as constant. So actually I can get rid of that. So we got so the derivative of 4y squared with respect to y, that's going to be 8y, because remember we bring this 2 down, multiply it by the 4 that's already there. So 8y plus 21y squared, right? 3 times 7 is 21, reduce the 3 by 1. So this one's a little different. Now we have e to the power of x minus y. This is the same as e to the power of -y plus x. So x is a constant now. So by the chain rule, this is going to be e to the -y plus x times the derivative of -y plus a constant. So it's going to be -y plus x, right? So this is going to be e to the -y plus x multiplied by, well, the derivative of this x is just 0, and the derivative of -y, or this isn't x, this is y. And the derivative of -y with respect to y is -1. So it's going to be negative e to the y plus x. And we had that 2 there, right? We already had that 2 there, so we had -2 out in front. If we're multiplying that by -1, that means we're going to be adding 2e to the x minus y. Okay, last step. Now we have to differentiate this entire inside with respect to x. Okay, so since there's no x's here and it's just, we can consider that a constant for now, that's going to be 0. The derivative of 8y with respect to x is 0. Same thing, 21y squared, there's no x in it, so that's just a constant, so it's 0. Plus, let's think here, we're differentiating this with respect to x. The x in here is positive, the y is a constant, so by chain rule, it's just going to be 2 times e to the x minus y. Okay, so that's your answer for this part right here, f sub x, y, x. Now let's do the same thing for f sub y, x, x, and see if it's the same thing. So I'm going to rewrite the function f of x, y. That was equal to 4y squared x plus 7, was it y cubed x? Xy cubed, yeah, I'll just write y cubed x plus, or sorry, minus 2 e to the x minus y. Okay. So now if we're trying to find, what was it, f sub yxx, remember this equals the partial derivative with respect to x of the partial derivative with respect to x of the partial derivative with respect to y. Okay, so the first thing we have to do is find, or this was partial f by partial y. So first we have to find partial f partial y. So y is our variable. That means that we're going to have to treat everything else that's not a y as constant. So this is going to be partial x, partial x of, well, there's a y squared in here, and then there's a 4x kind of sandwiching it. So if we bring this 2 out front and reduce the exponent by 1, it's going to be 8xy. Okay, then we're going to add, same thing here, bring the 3 down, multiply it into the 7, reduce the exponent by 1. So it's going to be 21, and then we still have this x attached, y squared. Okay, and now we're going to differentiate negative 2 times e to the x minus y with respect to y. Okay, so we found in the last question that that was going to be positive 2e to the power of x minus y, because we multiplied by the chain rule, right? We differentiated 2 times e to the x minus y by just multiplying 2 times e to the x minus y by negative 1, because the derivative of negative y with respect to y is negative 1. Okay, so now that we have this, we can differentiate it further with respect to x. So we still have this partial x on the outside. So now we're differentiating this stuff with respect to x. So x is our variable, everything else is constant. This is going to be 8y plus 21y squared plus 2 times e to the x minus y. Okay, last step. We're taking the partial derivative with respect to x of everything on the inside there. 8y doesn't have an x in it, so we can call that a constant. And the partial derivative with respect to x of a constant, or the ordinary derivative of a constant, is just 0. So it's going to be 0 plus, same thing here, 21y squared. Constant derivative of that is 0 plus the partial derivative with respect to x of 2 times e to the x minus y. That's just going to be 2e to the x minus y, because the partial derivative of x with respect to x is just 1. So we multiply that by 1. So your answer here is 2 times e to the x minus y. And remember, this answer here, that matches up with what we got right here, right? Because we had 0 plus 0 plus 2 times e to the x minus y. That's exactly what we had down here. 0 plus 0 plus 2 times e to the x minus y. So we kind of verified Clairaut's theorem here, and we don't have to stop with second degree partial differential equations. We can go further into third and fourth degree. So for example, if we were taking, or this was a third degree actually, we can also go into a fourth degree. So if we had f of x, y, x, x, right, we could say that was equal to f of y, x, x, x. And some proof for that is we, like, the way we write it, we work right to left in terms of writing the actual partials. So we go partial by partial x, okay, of, and then the next one is x as well. So partial with respect to x here. Next one is y. So partial with respect to y. And then the last one is x on the very left. So it's partial, or it's partial f actually with respect to x. Okay, and if we expanded this kind of almost algebraically, right, we have 1, 2, 3, 4 partials on the top. So this would equal partial to the fourth, right, of f divided by, we have, let's see here, we have how many x's on the bottom here? 1, 2, 3. So we'd have partial x squared, right? Partial y squared, right? Because we had, or no, it would be partial x cubed, and then partial y to the first. Okay, so this is another way to write it. It's not as intuitively obvious. It looks kind of messy and long and weird. But you'll see, like, I'll just write up here, we found this was partial to the fourth of f, partial x cubed, partial y. Okay, so now that we figured that out, let's do it with kind of the switched order. Okay, so the way I've written it here, f sub y x x x, right? We just kind of switch the order that the x's and y's are in. Okay, so the y is going to be on the very inside. So partial f by partial y. And then as we move to the left, we're just going to add an x here. So we're really taking partial by partial x of partial by partial x of partial by partial x of partial f by partial y. Okay, and if you do kind of the same algebraic method, there's 4 d's on the top with an f attached to it, so it's d to the 4th f. And then there's 1, 2, 3 x's and 1 y on the bottom. So it's going to be partial x cubed, partial y. And you'll see this is the same thing that we got up here, right? So the 3x's, 1y, when you kind of expand that out, it's going to be the same thing. Okay, and that's just Claro's theorem. It's also called Young's theorem sometimes too. It's the same idea. Okay. Okay, so for this question, compute each of the first order partial derivatives for h of w x y z equals sine of w plus x times cosine y minus z. Okay, so all we're doing is we're finding h sub x, h sub y, h sub, I'll do w first actually. H sub w, h sub x, h sub y, and h sub z. So what's the partial derivative of h with respect to w? Okay, so all this means is just partial derivative of h with respect to w. Okay, well, let's see here. The right side here is our function. Okay, if w is our variable, okay, then that means that everything else can be considered constant. So this cosine of y minus z, that can just be thought of as a number, so let's just bring it to the front here. Because we know when we're differentiating, the constants can just be factored out. Okay, so that's going to be times, what's the derivative of sine of w plus x? Well, we know that the derivative of sine is just cosine, okay? And we know that w is our variable, x is a constant, so the derivative of sine of a constant, or a variable plus a constant, is just itself, or sorry, it's cosine of that inside there. So it's going to be cosine of w plus x, right? Because by chain rule, we would have to multiply this quantity here by the derivative of the inside. So the derivative, not the partial, just the ordinary derivative with respect to w of w plus x is just, well, the derivative of w is 1 plus the derivative of x, which is 0. Okay, so it would just be 1. So essentially we're multiplying it by 1, so it wouldn't change. Okay, so this would be your answer here. Okay. So we're taking the partial derivative of h with respect to x. It's going to be the same answer, isn't it? Okay. It's going to be the same answer because x is kind of that thing we have in here. It's our variable. We're considering w to be constant. So since w is constant and x is our variable now, it's going to be the same thing. So it's going to be partial h, partial x, and I'm not even going to write it out. I'll just draw these lines here to symbolize it's the same thing. Okay, and then the partial derivative of h with respect to y, it's going to be kind of the same idea, except the sine of w plus x is our constant now, right? Because our variable is kind of the subscript here, y. So if our variable is y, that means this part is changing. This cosine of y minus c, that's the part of the function that's changing. Everything else is a constant, so we can just bring that out to the front here. Sine of w plus x or I'll be consistent with how I'm writing it out. This is going to be partial h by partial y. Okay, so like I said, that's going to be sine w plus x. We're considering that a constant, and we're multiplying it by the derivative of cosine of y minus z. Okay, so this is going to be times, what's the derivative of cosine? Well, the derivative of cosine is negative sine, so it's going to be times negative sine of y minus c, and then we have to multiply it by the derivative of y minus c with respect to y, and that's just y, right? Or sorry, that's just 1. So if we're multiplying it by 1, we don't even need to write that. So that's just going to be negative sine of y minus z times sine of w plus x. Okay, now let's do derivative of the partial derivative of h with respect to z. What's this going to be? Well, the sine of w plus x is still constant like it was before. So sine w plus x, that's our constant. Now we're multiplying by the derivative of cosine of y minus z with respect to z. So this is going to be cosine of y minus z. And then remember, we have to multiply this by the chain rule by the derivative of y minus z with respect to z. That's just going to be negative 1. Okay, so this can be written as, hold on a sec here. This should be negative cosine here, or negative sine, I mean. So this is negative sine, not positive cosine, because we have to take the derivative, and I just left it as cosine. So negative sine of y minus z times negative 1. So this is just sine of w plus x. And see how we have two negatives here? We have negative sine times negative 1. That's just going to give us positive sine. So we get positive sine y minus z. And we have to leave it as that. Even though these are both positive sine, we can't like combine the insides because they're not like terms, right? So yeah, that's a bit of a tougher equation, but kind of the same idea. It doesn't matter how high of an order of a derivative you're going, you're still kind of doing the same process. Okay, consider the function f of xy described by the table of values shown. Use the table to estimate the partial derivative of f with respect to x at the coordinate 1.1 and 3.6, and f sub y, so the partial derivative of f with respect to y at the same coordinate. Okay, so anytime we have an ordered pair in 3 dimensions, so this is f of xy, this is going to be our x coordinate, and this is going to be our y coordinate. Okay, so on this table of values here, the coordinate we're looking at is when x is 1.1, so that's right here, and when y is 3.6, so that's right here. So we're going to go across and see where those 2 points meet, and that's going to be right here. Okay. So this is kind of our point of interest, 9.278. And we're trying to find the rate at which the function is changing. I'll just erase this here. The rate at which the function is changing with respect to x at that point. Okay. So to estimate the partial derivative of f with respect to x, that's just going to be how f changes divided by how x changes. Okay, so x is this top column here, this top row, and it's increasing by increments of 0.1. So our dx, our delta x, it's not going to be infinitely small like it is with actual derivatives. We're never going to be exact when we're looking at tables of values, unless it's a straight line. But for functions like this, we're never going to be able to differentiate exactly because these increases would have to be infinitely small, right? That goes back to kind of the fundamentals of calculus and derivatives that we learned about before. So the smallest one we're going to kind of look at is 0.1 in the x direction. So if we go 0.1 in the x direction, if we go from 0.1, or if we go from 1.1 to 1.2, how does the value of our function change? So y is still 3.6, right? Because remember, this is f sub x, partial derivative of f with respect to x. So we're considering y a constant. That's why we're keeping it 3.6. But how does the function change as we kind of nudge 1 to the right? Okay, well, it goes from 9.278 to 9.499. So I'm going to give myself a bit more room here. This is our f2 minus f1. So f2 is 9.499 minus 9.278. And our delta x, that's just how much the x has changed. So that's just 0.1, but we can write it as 1.2, which is our new x value, minus 1.1, which is what we started with. This is the actual x value of our coordinate. Okay, so this is going to equal, I'm just get my calculator here. So 9.499 minus 9.278 is 0.221. And that's going to be divided by 0.1. So that's just like multiplying by 10. So that's 2.21. So this is the partial derivative of f with respect to x at the coordinate 1.1 and what was it, 3.6. Okay, and we can do it the other way. We don't have to nudge in the right, towards the right in the positive x. We could go from 1.1 to 1.0. Okay, and we should get approximately the same thing. So let's do the opposite here. I'll go f of x plus f of x minus, right? F of x minus, that's still delta f over delta x. But what if we went from 1.1 to 1.0? Or sorry, from 1. So 1.0 is first because that's our x2. So this is the x we started with, the x we're going to. So if we start here at x equals 1.1 and we kind of bump ourselves to the left one instead of to the right, our change in x is going to be negative 0.1. Okay, and how does the value of our function change? How does f change? Well, if we bump 1 to the left, that means our new point is here, and that's 9.057. So it's going to be 9.057 minus 9.278. Well, 9.057 minus 9.278, that's negative 0.221. So negative divided by negative, that's a positive. Those cancel. That's like 0.221 times 10, which is 2.21. So it doesn't matter which direction you go, you'll get approximately the same thing. That might not always be the exact same, like it was in this case, but they'll be approximately the same, all right? Now, the question's asking us to do the same thing with respect to y, okay? So we kind of changed our x and called y constant, but now let's change our y and call x constant. Okay, so if we do that, that means that x is always going to be 1.1. We're not too worried about it. I'm gonna erase this here. Actually, no, I'll keep it. I can just write it down here. So f sub y, that's going to be how the function changes for every unit that y changes. Okay, so we can kind of go down or up in the y direction. Doesn't really matter. Let's just go from 3.6 to 3.65. So that means our dy is 0.05. Okay. And if we go from 3.6 to 3.65, that means we're kind of nudging down. How does the value of the function f change? Well, it's going to be 9.871, which is the new f, minus 9.278. So that's 0.593. Okay, so 0.593, the value or the amount that f's changed for every 0.05 is going to be 0.593 divided by 0.05. So that's 11.86. So we're estimating that when y equals 3.6 and x equals 1.1, for every unit distance we go down or up in the y direction, the value of our function f is going to increase by 11.86 times that unit. Okay, and we can do the same thing. We can do the same thing, delta f over delta y, in the other direction. So instead of going from 3.6 here to 3.65, right, we can jump in the other direction to 3.55. So now our change in y, it's going to be negative 0.05. So how does f change as y gets smaller, in other words? Well, let's see. So if we started here, right, and we're jumping up y value, so we're decreasing the y value by 0.05, the f value is going to be 8.685. So now delta f is 8.685 minus, okay, minus what we started at, so 9.278. Minus 9.278, that's going to be negative 0.593. Okay, we divide that out, negatives cancel, we're going to get positive 11.86 again. So like I said, these aren't always going to be the same, but they're pretty much always going to be close as long as your dy and your dx is relatively small. So this isn't going to be your exact answer for what the partial derivative actually is. You need the equation to solve that, right? And we know how to do that, but that's kind of an estimate that you can use because these increments, these change of x and change in y's are relatively small. So yeah, so that's kind of the essence behind partial derivatives, first order, second order, third order, even fourth order, right, with that sine and cosine, the f of w, x, y, z, that crazy looking function there, and also evaluating partial derivatives using tables of values, which I think not lots of people are used to doing, but it kind of gives you an intuition behind what partial derivatives actually are, right? Because in the questions above, you might have been thinking like, well, why are we even keeping the other variables constant, like they're letters? I thought they were variables. But in this last question, you can see why we're calling them constant. Because if we were finding the partial derivative of f with respect to y, we're not changing this x, right? If say we're bumping our y up and say our new coordinate is here, our x coordinate is still 1.1, so our x is constant, right? The only thing changing is our y. That's our variable. Our x, even though it's a letter, it's still some number. Okay, we're not sure what that number is, but it's still a number. We can just treat it like a constant and solve it that way. Okay, so I hope this was kind of useful to you if you're learning about partial derivatives, just for fun or for your classes or wherever you may be learning it. But yeah, had fun talking about it, and I'll see you soon.